Hello everyone and welcome to this lecture. So one of the main topics we will cover this week is GAN networks, which are we introduced them briefly at the end of last week. Essentially, they're models where we're training two networks at the same time. One of them is a generator and the other one is called a discriminator. So before we really dive deep into this approach, it's important to learn more about competitive environments and how we design agents to perform this type of adversarial search and essentially in the process improve each other at whatever function they're doing. So today we're going to go back and introduce game theory and review how we train our agents to make optimal decisions in games. We will learn about min-max decisions, alpha-beta pruning, and multicolor tree search as well. Then we'll discuss resource limits and approximate evaluations. Then games of chance. Finally, if we have time, we'll do games of imperfect informations, and then the limitation on of game search algorithms. So first we want to cover competitive environments. Okay, so in which two or more agents have conflicting goals. Okay, so this is what we call adversarial search problems. So rather than deal with the chaos of real-world problems, we'll just focus on games. In this case, for example, chess or Go or poker. But essentially, what we discuss will be applied to much more realistic problems, obviously, to learn image generations and things like that. So for us, in AI, focusing on these simple games allows us to essentially learn the state of a game in a much easier way to represent it. In addition, agents are usually limited to a small number of actions they can take, unlike in real-world situations where agents have almost unlimited number of actions. And physical games like ice hockey, for example, have more complicated descriptions, so we can't really use them to introduce this topic we want to introduce. And they have a lot more possible actions, obviously almost an infinite number of actions. And also the rules are not very well defined. That's why I guess you have referees, because there's always some subjectivity in the process. So that's why we don't really focus on physical games, but rather on just simple games like chess or poker, something that is contained, has a limited number of actions that can be taken and can be the state of the game at any point can be easily described using a certain number of variables. So first, let's start with game theory. So there are three different approaches we can take to study multi-agent environments. The first approach is appropriate when there are a very large number of agents. In that case, we just consider their impact in the aggregate. For example, if you're studying the economy, in that case you have, of course, millions of people living in a country, so that's millions of agents. So it's much better to just aggregate their actions, which allow us to do things like predict, for example, that increasing demands will cause prices to rise without really having to focus on any individual agent. The second approach is to consider agents as just part of the environment. Essentially, part of the environment that makes the environment probabilistic or non-deterministic, because we can't really predict the actions of a given agent at any point in time. But if we model the adversaries in the same way, then we miss the idea that our agents are competing, right? They're actually essentially trying to defeat each other. So this approach will not work for us in that case. The third approach is to explicitly model the adversarial agents with the technique of adversarial game tree search. So in other words, we will begin with a restricted class of games and define the optimal move and an algorithm to find it. For example, min-max search. And then we will show that pruning makes the search more efficient. So pruning, you will see, essentially just limits the search space such that we don't spend forever for each agent investigating every possible move. Okay, so pruning will make the search a lot more efficient by ignoring essentially portions of the search tree that make no difference to the optimal move. And this is needed because in games like chess, for example, or Go, with billions of possible combinations or different passes along the search tree, we're never going to have enough time to find the absolute optimal move, even with pruning. And that's why we have to cut off the search at some point. Now, for each state where we choose to stop searching, we will ask who is winning. And to answer this question, we have a choice. We can apply a function, a heuristic function, which we call the evaluation function, to estimate who is winning based on the features of the current state. Or we can average the outcomes of many fast simulations of the game from that state all the way until the game ends. And then we can decide who is in a better position at this current state of the game. So the games that are most commonly studied within AI, like chess, for example, are games that are called deterministic. Two-player games, so they're deterministic games. The environment is well known, there's no element of randomness. They're two-player, they're turn-taking, so each player gets his turn, one after the other. They have perfect information, so at every point in time, we know the entire state of the game. They're zero-sum games, so for each winner, there's a loser. Now, perfect information is the same as saying fully observable. Okay, so there's nothing hidden, all the pieces are on the table, everyone can see everything. And zero-sum means that what is good for one player is just as bad for his opponent. So there's no win-win outcome possible in such games. So for games, we often use the term move instead of the term action. But in artificial intelligence, we usually take the word action for an agent. And when we say position in a game, the synonym for that in our field in AI is the state of the game. So the state of the game is a snapshot of the board with all the pieces on it and at any given point in time. So our two players, we'll call one of them Max and the other one Min. and you will see why in a minute. And typically Max moves first, and then the players will take turns until the game is over. Now at the end of the game, points are awarded to the winning player, and penalties are given to the loser. So a game can be formally defined then with the following elements. S0 is the initial state of the game. Okay, so that's essentially how the game is set up at the start. The function toMove returns the player who has to move at state S. Actions of state S, that's the set of all legal actions or moves that can be taken at that given state. Result, S of A, so that's the result of taking action A at state S. So that will be the transition model that results in a new state S after taking action A. Now we have the binary function isTerminal, which is a test essentially. Returns true if the game is over, and false if the game is not over yet, there's no winner yet. And the states where the game have ended are called terminal states. And finally, utility function, utility of S and P. So typically we call that the objective function when we're studying deep learning because that's what we're trying to maximize. This function defines the final numeric value to player P when the game ends in terminal state S. So in chess, the outcome is a win, loss, or draw. So the values of this function of the utility is either 1 for a win, 0 for a loss, or 1/2 for a draw. Some games have more possible terminal outcomes. For example, in backgammon, the payoffs are from 0 to 192.